All right, so here we go, going over the free energy and entropy ditto or worksheet. So let's do this. Now, of course, we're using some demonstrations we did, and we're thinking about the dancing gummy bear demo, and looking at the reaction before I dropped the gummy bears into the liquid potassium chlorate and saw the nice fire. Okay, I had potassium chlorate. Now, this is a molecule, or at least we're going to call it a particle. This is potassium, chlorine, and oxygen, and there's one potassium, one chlorine, and three oxygens with free energy is becoming potassium chlorate liquid. So if you notice, the chemical formula, one potassium, one chlorine, three oxygens becomes one potassium, one chlorine, and three oxygens. And so the only thing that's changing is that we have a solid going to a liquid, okay? So this is a physical change, and the reasoning is very simple, okay? We are essentially maintaining the same chemical formula, but changing only the phase. So we're just changing the solid phase into the liquid phase. This is a physical change because we're not changing the chemical formula. A chemical change is when we make a new substance with a new arrangement. Okay, so that's pretty simple. Physical change, solid to liquid. We're just melting this compound. We're not making a brand new substance because of the same chemical formula. Pretty simple stuff. Now let's get into some of this now. So is it endergonic or exergonic? Well, the thing that I know is that if there's free energy in the reactant side, now what the heck is the reactant side? Well, the reactant side is the side of the reaction, the process that's in front of the arrow. Think of the arrow as direction. We start with these reactants and we do what? We produce something called products, and there's a direction that tells us. Okay, so we know that essentially this reaction is taking this reactant solid and using free energy. Since the free energy is in the reactant side to the left of the arrow, I know that these or this is part of what's needed to go to the left. Okay, if we scroll down, we're going to see in some places the free energy on the right of the arrow, which we would say is that this is the reactant side, this is the product side. So now with the CO2 and the water, H2O, we also are producing free energy. So free energy is a product in this case. So in the case that we're looking at, is the free energy is a reactant, which means we need it. Okay, if we need it, that probably means that we're taking KClO3, which was in a test tube, so I'll draw a little tube here, and that's our system. Let's define our system. And what was happening? Well, heat was flowing into the system, okay? In fact, the heat that was needed, or the energy, in this case, the free energy that was needed, and there it is, there is the energy that was needed to make this happen. So we would say that this is an endergonic reaction because it's absorbing or consuming free energy. Now, a lot of people are going to say, what about regular energy? Well, yes, energy was flowing into, but clearly this process would not have occurred without my torch giving off the free energy that is basically what this liquid has now. Okay, so essentially we were putting the free energy. Now the free energy is a concentrated source. What was the concentrated source? Well, my friends, in bio, it was the torch. The torch, right, had a tip and the fire came out of the tip, and the source was, the concentrated source was the fuel in my torch. Okay, so I had fuel in the torch reacting with oxygen, and that heat, of course, went in there. So this is exergonic because free energy flowed into it, but it was what free energy was needed to make this process occur. Remember, exergonic, endergonic reactions are non-spontaneous until you provide the energy. So we needed to make this work. We had to basically force this to happen that didn't happen nonetheless. Look at the demo. It doesn't occur unless you add energy. Okay, now because it's endergonic and because free energy is flowing in, and I know that from the reaction or how it's written, energy is on the reactant side, we're going to say in terms of entropy, okay, well, let's leave this for a second. Let's go to spontaneous. I know that at 20 degrees Celsius at room temperature, this was a non-spontaneous process. And you should see something. If something is non-spontaneous, it's always going to be endergonic because what? Free energy is in the reactant side because you are absorbing it and it helps to draw. These will always go together. Now, in terms of a process that's endergonic, this is a tough little question here. What does the entropy do? Now, I'm going to answer it two ways. And I want you just, I should have done it this two ways, but let's think about it. Entropy is given the, basically the abbreviation of S. And I use delta S to show a change in entropy. Now, if we look at the entropy of just the system, okay, we think of the energy of just a system, what do we have? I've got a solid becoming a liquid. So I really should say what's happening to the entropy of the system. Well, if a solid, which is basically an arrangement of particles in a regular organized fashion called a crystal, became a liquid where they're not organized anymore and every individual molecule or particle is free to move, unlike in a solid, they're in a fixed position, we can say the delta S of the system in terms of the particles, okay, definitely increased. They got more random. Liquid particles are more random than solid. Now, if you said, Mr. Grodsky, what about the change of entropy in the universe? Okay, well, as you know, in order for a non-spontaneous endergonic process to occur, you have to couple it with something that's what? Exergonic. So the torch, okay, right here, basically did the work to make this into a liquid, gave the energy, the free energy flowed from the concentrated source. And anytime you use a spontaneous process to drive, make this work this way, and this free energy is telling me it came from something spontaneous, okay, some of that energy in the spontaneous process had to escape as heat. So you could say that the delta S of the universe increased. So both of these would be fine for me. In terms of the system, there's an increase because the chemicals are now free to move. In terms of the universe, the entropy is increasing because the what? The spontaneous part that delivered the free energy has to give off some heat because spontaneous process by definition have to disperse some heat in order to work. So in essence, not all of the free energy from the torch, okay, was accepted by the potassium chloride. Some of it escaped as thermal energy that dispersed outward. So that's how you can say the delta S of the universe increased. So this question can be both ways. If you consider the molecules, okay, if you consider the molecules, easy. If you consider the overall energy change with the spontaneous process that delivered the free energy, you could say that the entropy increased, okay? So let me explain. Again, one more time. The system's entropy, okay, increased, and you can also say that the entropy of the universe also increased when you consider the energy that has to dissipate, all right? So both of those are fine. I know some people want to say, well, the entropy decreased, okay, because it's non-spontaneous. But remember, it's now working because of a spontaneous problem. So again, we're forcing it to happen, and we're using a spontaneous process. The best answer here is that there's an increase in entropy in terms of the particles and in terms of the free energy because of the spontaneous process, okay, that's giving off heat. Moving forward, okay, same idea. If you notice the next one, we took the liquid potassium chlorate, all right, that kind of gained some free energy, all right, and where did it gain the free energy from? Well, the hot liquid, okay, and it basically breaks apart into two new compounds. Why is this a chemical change? Well, because new chemical formulas are being made. And how do I know? Well, we're starting with 1K, 1 Cl, that's chlorine, and 3 oxygens. And now we have a particle. We have 2 of these KCl particles and 3 of these O2 particles. We're making brand new chemical formulas. And when you make brand new chemical formulas, okay, you're going to have new properties and new things happen. All right? Whereas in this one above here was a physical change. We have the same compound, same type of particles, so there wasn't really any new properties other than it having more thermal energy. Okay, now, what do I know? Well, because the free energy is in the reactant side, that means I'm taking in the free energy, it has to be endergonic. And what does that mean? That means that my free energy in the system is going up. I'm absorbing it. And it also means that it's a non-spontaneous process at 20 degrees. This would not occur at 20 degrees because this needs to be a liquid. And what maintains the liquid state is the free energy that was given to the torch. So endergonic and non-spontaneous go together. Okay, now, what about the entropy? Well, in terms of delta S of the system, the molecules only, we have 2 of these big particles breaking down into what? A total of 5 smaller particles. So if big things break apart into more pieces, okay, 2 big things into 5 smaller pieces, would you say that these have more degrees of freedom now and there is an increase of disorder in terms of the molecules? And you'd be right. So you could say there's an increase in entropy of the system because you're doing what? Liberating the molecules. Now, in terms of the universe, well, some of the free energy doesn't all get to the KCl. Some of it's dissipated as heat. So you can also say it's increasing because of the spontaneous process. The heat delivered by the torch maintain that. Some of that heat doesn't get to this because it escapes as heat. So both of that would occur. So we don't say that entropy really decreases, although I know why you would say that. Okay? Again, think about the system, think about the universe, the spontaneous process drives it. All right? Now after I had this liquefied potassium chlorate that broke apart into KCl and oxygen, the oxygen that I was making was in the tube, and a lot of it. Then I dropped a gummy bear. Now, a gummy bear is a disaccharide. It's a sugar. And here's our chemical reaction. How do I know it's a chemical reaction? Because I'm making what? Brand new chemical formulas. I have this huge disaccharide and a bunch of oxygen molecules, and now I'm making CO2, which, by the way, if I didn't tell you, is a gas here, and this is a gas. This is a solid, and this is a gas. I should have put my states of matter there. So in any case, I have a compound that has 12 carbons locked into a solid, just rotating. And now through the reaction, I'm liberating 12 individual carbons as molecules of CO2. CO2 is 1 carbon double bonded to an O on both sides. We'll get to this at some point. But this is a smaller, freer molecule. So we've got big carbon dioxide solid that barely moves, and we're making 12 gas molecules that can fly around. So the delta S of the system, just in terms of the molecules dispersing, is increasing. And look at the energy. Look where the energy is. The energy is on the product side. This is the product side. So what does that mean? I'm making 12 independent CO2s flying around, a lot of water's gas flying around, gas, and I'm also producing free energy, okay, that's leaving the system. Okay, now who is it leaving from? It's leaving from the stored energy here. Okay, now for those that are not getting that, if it's an exergonic and we're releasing free energy, that means that the reactant, here's the reactant's free energy, becomes the product's free energy. It drops. Why? Because we're producing or releasing the free energy, okay, and that free energy could do some work, or it can be just dissipated into the environment that never ever can be reused again. So you see the free energy here. It means that it's being liberated from the original reactant. The ones above here, Endergonic, you're starting with low free energy and you're going to a system of high, and the only reason that works is because free energy is going in, okay, where here free energy is leaving. Important. Okay. So what we're going to do here is draw an energy diagram for the chemical reaction below. And this is something that's a little bit new, so I want you to just pay attention as I do this. All right? We've been drawing kind of a bar graph, but we're going to kind of make this a little more, build this up a little bit. Very simple. Just follow along. Okay, so we first know something. We know that it's in this case, exergonic because energy is being released. Okay? Which means this is a spontaneous problem. You notice there's no free energy in the reactant to force to happen, unlike the two above. These guys were never going to react by themselves because they had free energy that was in the reactant side to drive and force the reaction. This didn't need it because it had stored free energy. So that's important. And of course, the entropy change is going to essentially increase because we're making more free molecules and we're releasing free energy outward that can be used to make the molecules of the universe go faster, and we're dissipating the heat. So that's important. But I know that it's exergonic, heat's being released. I know it's spontaneous. I don't see heat in the product side. So what I'm going to do is I'm going to start with a line that's high. Okay? Now, this right here, we'll just color code it. This represents, assuming my line goes all the way down, not sure why there's a break there. This is the free energy, I just do free energy, Fe, of the reactants. So this line all the way up, so this is how much free energy we have of the reactants. Okay, and by the way, this is the free energy of the system. The reaction is the system. And another way to say free energy is G. And a change of G is a change of free energy. Okay, so now I start there. I'm going to also finish lower. Why am I finishing lower? Because energy was released. I see it's produced. It's produced as a product, means released, just like these gas molecules are released. So I'm starting lower. And of course, this is going to be, from here to the bottom, the free energy of the products. Okay, so I get rid of this guy and this guy. Now, how does the reactants become the products? They don't just do this. This is not what happens. We just don't go from here to here. Because if this was the case, reactions would always go and never be not reacting. Notice I needed a little spark for the whoosh bottle, right? The whoosh bottle, I put the alcohol vapors in and I put a spark, and the spark started the reaction, and then it went by itself and gave the whoosh sound, okay? And it wasn't reacting until I added a spark, which means all reactions have something called an energy barrier. And I'm going to draw it here. So in order for this to react, what actually happens when we plot the free energy change, it looks something like this. Now, let me explain what's happening. This is the highest peak, and we're going to call this the activated complex. So I'm just going to make it AC for all intents and purposes. Now, what's the activated complex? Well, what are the reactants? The reactants are basically the sugar and the oxygen. As I mentioned before, for these to react, they have to collide. So here's my sugar, and then here's my oxygen. They're going to collide. And when they collide, there comes a point where they repel each other a little bit because they have something called electrons on the outside of them. But it's kind of a place where, if I zoom in, they're just about ready to do something. They just got close enough. See, on the outside of molecules are these negatively charged particles. And the outside of this oxygen, being much smaller, is also negatively charged. So we know the things that are negative, well, guess what? Repel each other. Like charges repel. So how do we get these guys to what? Combine to form a reaction. We have to give them enough energy, kinetic energy, to overcome their repulsive forces. Again, each molecule, whether it's the sugar here or the oxygen, have electrons on the outside. So for them to react, they have to physically collide. In order to collide, they have to have enough kinetic energy to overcome their repulsive forces. So if you notice right here, this top of the hill all the way down, point all the way down, represents the maximum energy due to repulsions that we have to overcome to make this work. So from the top of the hill all the way down, this right here represents the activation energy. We call it EA. And that's the energy barrier. What does that mean? For these reactants to become products, they have to first absorb some energy to get past this sticking point, okay, this repulsive point, okay, this nervous energy point. And once they get past this, the energy moves. It's kind of like sliding down a hill. If you have a slide, whee! In order to what? Ride the slide, you have to climb the slide. There's no way about it. Unless you're as big as me and you can just step over it, okay? And I can just ride it down because I'm big enough. But most of us have to climb the slide. But same thing with reactants. Even if they have a high, free energy, they're going to need some energy to get to the top. And that's called activation energy. And if you remember what that was the spark I put in the what? In the whoosh bottle. Okay? So that's the energy. So from here all the way up represents the energy of my activation energy. That's the energy needed to start the reaction to ride the slide. Once I get to the tippy top, it goes by itself spontaneously. All chemical reactions require activation energy. No ifs, ands, or buts. Some more than others. Okay? Now, once we slide all the way down into a more stable, low energy position, we make our products. Now, we're going to call the breaking down of sugar, okay, catabolic. We should know that from our discussion with lac operon. And this is a catabolic process. And so I'm drawing the energy diagram and place the reactants in appropriate. So delta G, which is what? The change in free energy, we're going to say is what? Well, delta G is the change. That is going to be here. We started here. Let's get rid of my slide. So the difference of where we start and where we finish. So I'm just drawing a dotted line to show where we started, and this is where we're finishing. So this difference right here is the change in free energy. And notice we're starting high, and we're doing what? We're going down. So delta G in this case is going to be negative. And of course it's negative. Free energy is dropping. Why? Because some of it's being released as heat. Why? Because it's exergonic. Why? Because it's a spontaneous process. And the what? The stored chemical free energy in the reactants is now lowered. So guess what, party people? The energy is dispersed. Some of the free energy goes to heat. Okay? Now, one little thing that we're going to use tomorrow is that we're going to start adding enzymes. And we're going to add enzymes to reactions. And we're going to learn that an enzyme helps facilitate chemical reactions. We have learned so far that enzymes are made and coded, are coded for by our DNA. They're transcribed by the messenger RNA. They're translated into amino acids at the ribosomes, okay, using the messenger RNA and tRNA. And these proteins, after they fold, okay, into their shapes based upon the what? The R groups. My God, we learned a lot. They have a three-dimensional shape, and what they do is they help reactions go better. And what they actually do is the activation with a catalyst or an enzyme does something very special. So we'll get a nice scale. What it does is it lowers the energy barrier. And you say, what? Yeah, the activation catalyst actually finds a pathway that makes the reaction start, but at a lower temperature, okay? Or a lower what? Activation energy. So this was the activation energy without a catalyst. Look at this little line. That's the activation energy with a catalyst. So I have to draw that little line. So that line is lowered. Now, what does that mean? Well, me and you are going to have a race. We're going to ride a big slide, and I'm going to ride a small slide. We're going to see how many rides we get in the same time periods. Because you have to climb up a lot more than I do, obviously, if we have a race in 10 minutes and see how many rides we get, and because I don't have to climb up, I can just, just kind of sit there and move over. But the point being is that we're going to see how many rides we get. I'm going to get a lot more rides because my hill is smaller to climb in the same time frame. So we speed up, okay? Catalysts facilitate reactions because a lot of times they speed up the reaction because they get more rides in, more what? More reactants can go forward faster because the three-dimensional shape of the protein helps them lower the cost to start the reaction, okay? If you think about our internal temperature of our body is about 37 degrees Celsius. That's pretty warm. That means our molecules in our body have a good amount of motion. If we're trying for a reactant, let's say the sugar, the disaccharide, to hit the oxygen in our bodies, let's pretend that's in our bodies like that. I'm glad it's not. Okay, they're going to collide with pretty good impact, but keeping temperature constant, if I have a three-dimensional enzyme that will help these guys collide with each other faster, okay, by kind of having a shape that collects both of them, then they won't need so many more collisions to react. So an enzyme, what it does three-dimensionally, it'll collect by the shape of the protein one of the reactants, and just by moving around, it'll have a shape to collect the other reactant, and right there, booyah, a bond can form. So a three-dimensional enzyme, a protein that folds in a certain shape, will actually collect the reactants and help them bring them together. And remember, in our body, we have so much stuff going on. An enzyme will really help these guys find each other, and therefore you wouldn't need as much random collisions, and the energy drops, and more of these will react. So that's why it's lowered. But you should think about this. If I have a pimple, I medicate it. And medicating a pimple is kind of like adding a catalyst. It's a medicated hump, all right? So if you have a hump, you medicate it. So this is the uncatalyzed hump, unmedicated, and here is the catalyzed, all right? Any case, moving forward. Thank gosh, right? So what provided the energy to overcome the reaction? Oop, let's go back. What provided the energy to overcome the reaction barrier? Okay, well, in this reaction, it was the spark, right? No, in this reaction, I'm sorry, this is the disaccharide. Probably it was the heat of the solution, right? Don't forget, the solution was pretty hot. We added heat, so we had a very hot potassium chlorate liquid, ClO3 liquid. So it provided the energy to overcome the reaction barrier, to start the reaction, to get to this position, was probably the high temperature of this solution, which of course was made by the spontaneous process of the torch, giving some free energy to this. Okay, so let's move forward. This was the cool demo I did today. And if you noticed, let's revisit what's happening here. We had a Christmas. We had a beaker, big finger errors here. We had a beaker of some solids. They weren't black, but hey, I'm limited by my color schemes here. So I had a, okay, let's do that. We had our compounds that were mixed together. We had a board. Hopefully I'm not doing that to you. And we had some water. That was red, why not? Okay, any case, all right. We put energy flowed how to make this occur? Well, we know energy came from the water, had to flow upward. How do I know? Well, the H2O underneath liquid became a H2O gas. So in order for a liquid who has so much more energy than become a gas, it has to lose its energy. So who pulled the energy away? Well, these chemicals, when they reacted spontaneously, okay, watch out, okay, they grabbed onto the heat from the water. So they pulled heat from the water or the environment. They took heat from the water or the heat from the air, probably in all directions, but water was definitely lost a lot. So heat lost or gained by the surroundings. The surroundings, which included the water, the air, your hand, okay, did what? Heat was basically lost by the surroundings. How do I know? The temperature dropped. That thing was very cold, hence my pun. Okay. Heat was lost gained by the system. Well, the system is the chemicals in this beaker, as we will define, and we'll say that heat was gained by the system. Okay? Now, the heat that was gained was put to work to make the reaction, okay, was put to work to make the reaction go. All right. Now, is there a decrease and increase in the entropy of the surroundings? Thank gosh I was more specific in this part of the worksheet. And the answer is, okay, well, all right, yes, I'm still at school. So yes, all right, if energy is flowing out of the environment or surroundings into the beaker, then we're losing heat or energy. If we're losing energy, the gas molecules that are flying outside us are going to start moving slower. Therefore, they're not going to be as what? Dispersed. So we would say at this point, there's a decrease of entropy in the surroundings. Now, we're not talking about the universe, just the surroundings, right? Has to be. We're pulling energy away from the air. The air is colder. Gases want to go fast and disperse in all directions. If they go slower, they'll stay around each other more. And therefore, they're not as what? As dispersed. Entropy is a measure of the randomness, dispersion of energy. Okay? So we would say that there is a decrease in the entropy. There's less dispersion. Okay? So heat is lost by the gained by the system. There's a decrease in entropy of the surroundings. What about the entropy of the system? That's interesting. That's important. When I look at the system, as I said before, I've got to look at the molecules. Now the system, okay, now the water is considered to be part of the surroundings. So the system's in the beaker. Look what I have here. This is a solid. These are two solids. And what did I make? Another solid, okay. But I made 10 water molecules and 2 gases. So overall, 2 big particles made 10 plus 2 plus 1, 13 smaller particles, by which 12 of them are not solids, including 2 gases. So clearly, 2 things breaking apart into 13, we would say that there is clearly going to be an increase in the entropy of the system. Now, when we say the system, we're talking about in terms of what? In terms of the particles' randomness. Particles that are more random mean they're becoming gases from liquids or solids, and there's more of them. So just due to particles separating, we can say that the entropy is increasing because particles being freer and having more freedoms to move is a dispersion of energy. Okay, hope you see that. So we have a conundrum here, don't we? We do have a conundrum here. We have a decrease of entropy in the surroundings because we lost some heat, and then we have an increase because we're making 13 particles from 2, some of them liquids and gases from 2 solids. So how do we know if we're endergonic or exergonic? Well, we definitely know that the process was spontaneous because all I did was mix 2 solids. All right, so I know it was spontaneous, so that would tell me it's exergonic, but I need to make sense of the entropy problems. Well, my friends, Gibbs free energy, delta G, is free energy. Okay, and there are 2 parts to free energy because free energy means what? Dispersion of energy, but there's 2 types of dispersion of energy. The one type is the heat flow. If the heat flows out, molecules move faster in the atmosphere. Hey, energy is dispersed. If energy flows into, like in the case of my reaction, the cool reaction, the universe gets cooler, like I'm trying to be. Never going to happen, but I keep trying. In any case, gases move slower and they're less random. They're less. So this is a conundrum. So we have heat as part going into and out of a system, and we have the entropy. Now this delta S written in this part of the reaction is for the system, which means it's for the looking at the particles. So let's look at our conundrum. What is our change in heat in our system? Well, here's our system. Diagrams help. Here's my system. That was the beaker. Okay, and what did the heat do? The heat flowed in. Had to, because the environment got colder. So cold, some of the environment froze. That was the water. Okay, we put the heat on the reactant side to show that heat is flowing in. Okay, so because energy is going in, the Q, the heat, okay, of the system is increasing. We're going to write a positive value here. All right, now temperature, we're going to just leave that alone. And now we're going to do the delta S of the system. Is the entropy of the system in terms of the particles increasing? Of course it is. 2 big particles make 13 smaller particles. That's dispersion of particles and energy. So we say that the entropy increased in terms of the particles. That's what the delta S is. There's a minus here. Now what did we learn in mathematics? You do plus the negative. So when you have a plus and a negative, the only way for this to be spontaneous if delta G equals negative. Why? This is free energy. What does free energy look like when it's negative? Hello, hello, right there. We start high and we go low. So this is a spontaneous process. So delta G has to be negative because we're going down. Delta G is negative. Starting high, going low. Imagine it goes together. Now, so for this to be negative, to show it's spontaneous, and it is, it must mean, party people, that we have a good thing and a bad thing. The good thing is that I have an increase in entropy due to my particles. 2 particles, okay, oops, I counted wrong. 3, I didn't say a 2 there. 3 particles making 13. Okay, so clearly there's an increase in entropy, and there's an entropy that's good. So this part right here is good. I'm increasing the entropy of the universe, okay, by my particles separating. This is bad. What's bad about this is my delta H is positive. Why is it positive? Because energy is flowing in. That's bad, as we spoke about. So therefore, to figure out our delta G and using our 2 components, all right, we can see that a positive plus a negative only becomes a negative if this negative is bigger. And what does that mean? That means if the particles entropy, the delta S of the system, okay, is bigger, if the entropy of the system increases more then the decrease in entropy because of the heat loss, this will be a negative number, okay? So they would call this an entropy-driven reaction, but that's how it works. It's a combination of heat flow and the particles, and that's how we use the formula. So delta G here is going to be a negative number. Why? Well, I know it reacted, but because I know it reacted and it did work, that this had to compensate, all right? Delta S in the universe, definitely positive. It increased. Why did it increase? Well, it had to. It's a exergonic reaction. It's spontaneous. Why did it increase? Because the particles, 3 big particles, became 13 smaller ones. And that dispersion of particle motion was enough to overcome the what? Heat that made the molecules slower. This was a bigger event that drove it, okay? Clearly this is exergonic. It's spontaneous, okay? Now, a consequence of the first reaction is that we made liquid go into a solid and it released energy. How do I know it released energy? Now, we didn't say free energy, because if this is the water, it lost energy to the system, lost so much energy, became a solid. Is this a chemical or a physical? Clearly, it's a physical. All right. Not sure why I did that. I faked myself out. How do I know? The chemical change stays constant. Is it spontaneous at 20 degrees Celsius? It is non-spontaneous. Water does not freeze, go to a liquid to a solid at 20 degrees Celsius unless it is forced to. Someone did some work on the water. So if we draw ourselves a diagram, this being the beaker with the chemicals in it, I guess we're going to make them black. And this is the water underneath. All right. And we know the heat flowed from the H2O, the water, to the chemicals. That's the only way it can happen. So we would say the heat is lost or gained by the surrounding. Well, we'd say heat is gained by the surroundings. The surroundings are now the beaker. The water is now the system. That's how we have to look at it now. Okay. And of course, the heat is lost by the system. So we know that delta H is negative here. All right. If this worked this way. Now, there's an increase or decrease entropy of the surroundings. Well, the surroundings, because they gain some heat, the gas molecules, or at least these molecules, they grabbed the heat and they did something when they became disorganized. And we know what that happened. What they did is they became from 3 particles, 13. And so we know that there's some disorganization that occurs because of that energy that flowed. So we would say that the entropy of the surroundings definitely increased. Whatever happened in the beaker became more random, okay? And now, what about the system, okay? The system, in terms of the entropy of the system, we know that we're dealing with liquid molecules, and liquid molecules move pretty randomly. They attract each other somewhat, but they move pretty randomly. And of course, when they become a solid, they become in a fixed position in a crystal formation, a 3-dimensional arrangement that's very organized. So when they go that way, you can see that just by looking at the particles' entropy, the delta S, is a decrease in entropy in terms of the particles. So this would be a decrease in entropy. So when we look at the values, we have a negative minus a minus. And when you do the math, we do plus plus. Let's make it plus plus. And so for this to work, and of course we did recognize the fact that by itself it shouldn't work. Water would never freeze at 20. But what is pulling the heat here in this instant as a consequence to the reaction inside, the chemical reaction, is that the reaction pulled heat from the water that normally wouldn't occur. So you're right, water is not going to freeze at 20 by itself. So normally it is non-spontaneous. Okay, normally it's non-spontaneous. Okay, but in this case, in this consequence of energy coupling by putting a exergonic reaction, okay, the free energy of the reaction above pulled energy from. So although it's non-spontaneous at 20, okay, it practically was forced to become spontaneous. The process is non-spontaneous, yes, but it was forced to happen by the free energy. So we're going to say that it was forced to happen, and because it was forced to happen, delta G is going to be negative. Now, if we didn't have the free energy of the reaction, and I had water sitting by itself, okay, this would be still written the same way. Energy has to be released in order for the water to become a solid. This would be non-spontaneous, and this would have to be a positive value. If water was hanging out by itself at 20 degrees Celsius, it would never freeze, and this would be positive. But because we're coupling, we're using the free energy of the what? Of the other reaction to force the heat. This is going to become negative. Okay, we know it because it happened. We saw the water freeze. It wasn't spontaneous, but we forced it to happen. So what happened, party people, is that what drove this reaction? To be negative, it must mean that delta H must be what? Great enough, meaning the heat released from the water was so high to cause the surroundings entropy to increase so much that it kind of did what? Overtook the loss of entropy, okay, the negative loss of entropy of the particles forming a crystalline solid. So this part of free energy is due to the energy loss. It's a good thing. Losing energy means the surroundings gain heat, and heat makes the molecules in the surrounding go faster. In this case, made the reaction go from 3 particles to 13. But this part is bad. Bad delta S, because we have what? Liquids that have free energy becoming what? Less free energy. And that's why energy is released. But this is bad. We're getting more organized. So this good entropy of the heat is big enough, if this value is big enough, to overcome this lack of entropy, and that's what makes it work. If the reaction did not pull enough energy, it would have not froze. So delta G is going to be negative in this case because we saw it happen, but it was made to happen because we used a what? The free energy of a what? Spontaneous reaction to force this to happen. And during the process, we lost some heat. Delta S in the universe definitely increased, okay, enough to make it happen. And now the process, I know it's non-spontaneous at 20 by itself, but with the what? With the other chemical forcing it to happen, we're going to say that it is now exergonic. It was made to be exergonic because this increased. And again, it would not occur unless this reaction was there. If this wasn't here, delta G would be positive, delta S would go down, and it'd be endergonic. What made all of this negative and work is because of coupling. We had a what? We had a spontaneous reaction drive a non-spontaneous reaction. And we know that all of the free energy that the spontaneous process had did not go to the non-spontaneous. Some of it got released as heat. And so therefore, we have an increase. Okay? So I know, hopefully this helped. I don't know if it helped, but hopefully it did.